Well, this lecture, according to my reckoning, is about the QR and QL algorithms. And so I want to do some of the theoretical background first, and it'll probably take the greater part of this lecture. It wouldn't be right, I think, to discuss the QR algorithm without saying something about the LR algorithm, so I shall write up the theory of them to some extent pari passu in English, and then later on concentrate a little bit more on the QR algorithm itself. The QR algorithm has a very long history. Many people have contributed to it over the years, but I think there were only two people who made the outstanding contributions. The first is Ruetishauser, when he proposed the LR algorithm, I think probably back in 1956, and Francis, who proposed the QR algorithm, which is a development of it, in 1959. Those, I think, were the two key contributions to the theory, though without all the contributions made since, it wouldn't be the algorithm that it now is. Well, what are they? What are the two algorithms, essentially? They start off with a matrix A, and for the moment it will be a general matrix, possibly even complex. You can factorize that in the form QR, where Q is unitary and R is upper triangular, or you can factorize it in the form A equals LR, where L is lower triangular and R is upper triangular. This being, of course, the LR algorithm, and this the QR. Now, we can say immediately one advantage the QR algorithm has: this decomposition always exists and is in some sense stable. The LR decomposition may not exist at all, even when A is quite a satisfactory matrix, from the point quite a well-conditioned matrix. And so already you have to start hedging your bets when you're talking about this algorithm. I shall have suffixes on them. I'm going to produce a sequence of matrices by both techniques. Well, now, if you take the matrix A2, which is R2, Q2, or A2, which is R2, L2, we see that, in fact, A2 is, sorry, that was really going ahead rather fast. R1, L1. A2 is, in fact, R1, which is Q1H times A1 times Q1. So that the second matrix in the series is a unitary similarity transform of the first matrix. And similarly here, we have that A2 is R1, which is L1 minus 1 A1 times L1. So here, A2 is again similarity transformation via the matrix L. Well, we can form a sequence of matrices where, in general, AS is QS RS, and RS QS is AS plus 1. And similarly here, we have that AS equals LS RS, RS LS equals AS plus 1. Now, we see from this last result that AS plus 1 is QSH AS times QS, which is the result I obtained up there for the first step. And now I can write in for AS, similarly, that is QS minus 1H AS minus 1 times QS minus 1 times QS. And continuing in this way, we see that the S plus 1th matrix in this sequence is equal to a transform of A1, and we get the product of the Q's, Q1, Q2, QS here, and on the right-hand side, on the left-hand side, we get Q1, Q2, up to QS times H. So all the matrices in the sequence are unitarily similar to the first one, and they're similar via the product of the Q's. And here you get exactly a similar result. The L's are always taking the place of the Q's, so that the analysis runs through pretty well the same on the two techniques. Well, it's convenient to have a notation. From now on, I'll concentrate on the QR algorithm. It's convenient to have a notation for the product of the first SQs, and I shall write that as big QS, and for the product of the Rs, and I shall write that as big RS. And so this result here is that AS plus 1 is a big QSH A1 times big QS. Now we want to get some idea. Ruetishauser put forward this proposal for the LR algorithm, and he proved that under certain circumstances the matrices AS converged gradually to upper triangular form. They're all similar to the original one, and when we've got to upper triangular form to working accuracy, there are the eigenvalues sitting on the diagonal. He proved first that this would, the sort of basic result he had was that this would happen in general when A1 has distinct eigenvalues rather of distinct modulus, and then he showed that in general it would tend to upper triangular form with the eigenvalues, which will of course occur on the diagonal, in strictly order of decreasing absolute magnitude, except in rather special cases of probability 0, when you might get some disordering of the eigenvalues. And the history of the theory of the thing has been really a gradual sharpening up of the results that Ruetishauser had in the first place, and getting rid of all the awkward points you have in the LR because of the non-existence of factorizations and their instability. Most of those disappear. The failure for decompositions to exist and the numerical instability disappears, of course, in the QR algorithm because of the basic stability of this factorization. Well, the most important point in the proof of the convergence is if we consider a big QS times big RS, by definition this is big QS minus 1 times QS. That is, of course, the recursive definition of QS itself. And this is RS, big RS is big RS, small RS times large RS minus 1. And QSRS is AS, and so this is big QS minus 1 AS times big RS minus 1. Now, if we apply this formula, we take this formula for S is equals S minus 1, we have that AS is equal to big QS minus 1H A1 times big QS minus 1. And taking this QS minus 1 on the other side, I have QS minus 1 times AS is A1 times QS minus 1. So here we have big QS, big RS is A1 times the thing with one index lower, which of course is equal to A1 squared times big QS minus 2, big RS minus 2. And continuing in that way, it's equal to A1 to the S. So we have the basic result here that A1 to the big QS times big RS is A1 to the S. And we see now immediately that the QR algorithm is related to the, in some sort of way, to the power method. And this is the result that one uses to establish the convergence of Q, and then the convergence of Q, and then hence ultimately the convergence of AS. Perhaps I could just sketch that. The interesting thing, it turns out at this stage to relate the QR algorithm with the power method applied directly to A. In the lecture, I should show that it's really related in a very important way to the inverse power method. but we'll leave that on one side for the moment. I'll sketch now the nature of the proofs. So I'll just do the simplest case, and I'll assume that A1 can be represented, reduced to diagonal form, and that A1 is in fact x times the diagonal, which is lambda I, times y. Y will of course be x minus 1, but it's not convenient to take advantage of that. And A1 to the s will be equal to x d to the s y. Now that follows from the fact that y really is x minus 1. And one uses this result to establish the convergence. I know that A1s is qs, big QS by big RS, is x d to the s y. Well now, there's only one QR factorization of a matrix, and this is the factorization which arises from the QR algorithm. I want to get that factorization by some other technique now, and of course the point is that those two factorizations will be the same. In this D, I can take the elements to be arranged in order of decreasing absolute magnitude, because the x and y can always be, columns of x and rows of y can always be arranged so that that is true. So that in this representation, I assume that that's been done. And now I try to expose the QR factorization of that in some other way. Well, I do it like this. I take x d to the s and let ly ry be the LR factorization of y. It's interesting, it's the LR factorization that is relevant here of y and not the QR factorization. And now I write that in the form x d to the s ly d to the minus s d to the plus s ry. And of course this bit at the end is still upper triangular. This is a diagonal times an upper triangular matrix, so it's still upper triangular. It's still upper triangular. And now if we look at this matrix here, it is ds ly d minus s. D is the diagonal matrix consisting of the eigenvalues in decreasing order of decreasing absolute magnitude. And if we look at this matrix, we find that it's still a unit lower triangular matrix. And the typical element in the ij position is lambda I to the s Lij over lambda j to the s. And of course this matrix is lower triangular, so the upper elements are 0. Well now, the lambda the elements in the subdiagonal of a triangle have I bigger than j, and so you've got lambda I over lambda j here. That's less than 1. And therefore, as s tends to 0, this all subdiagonal elements here are tending to 0. And so what you get here is x times a matrix, which, not to go into it in too much detail, is in fact tending to I. And this is d to the s ry. And so if now you do the QR factorization of x, you get ultimately QR d to the s ry. I'm just fudging over a little bit the limiting process, but I think it's fairly easy to see how it will go here. And so this is the QR factorization of A1 to the s, provided implicitly by the QR algorithm. This is another QR factorization of it, and they must be the same. That is upper triangular, and therefore QS, big QS, tends to Q, where Q is the matrix obtained by the QR factorization of X. Well, now let's see what that implies for AS plus 1. We have that AS plus 1 is AS plus 1 is QSH times A1 times QS, which is a QSH times X times A1 times x minus 1 times qs. Now, the qs is tending to q the factor of, we have that x equals qr. Qs is tending to this q. QHX equals r, and therefore QSHX is tending to r. So this thing here is tending to r. Sorry, this should be xd. A1 is xd, x minus 1. This is tending to r. We have the diagonal here. This is the reciprocal of that, so that's tending to r minus 1. And so I have a triangle times d, which is the lambda i's ordered in decreasing absolute magnitude, times r minus 1. And if you multiply them together, it's upper triangular with the lambdas on the diagonal. So that's the basic idea of it, and we see, rather disappointingly, that the QR algorithm leads to a sequence of matrices that are tending to upper triangular form with ultimately the eigenvalues on the diagonal, and the speed of convergence is really related to the speed at which the lambda I over lambda j to the s tends to 0, and therefore if eigenvalues are close, the convergence is rather slow. Well, this at first sight, much the same result comes in the LR algorithm. One can show in exactly the same way that in the LR algorithm, except for the possibility of breakdown because non-existence of factorizations, again, AS is tending to upper triangular form, and the speed depends on the speed at which these things come to 0. So I must confess, when I first saw the LR algorithm, which was probably around about 1956, I wasn't very impressed with it. It seemed an interesting algorithm, but not a very practical one. If you look at it as it was described, each step consists of the LR or QR factorization of a matrix that requires 1/3 n cubed operations. Then you have to multiply them in the reverse order. So the single step is really quite expensive, and after all that, the speed of convergence is just that of the power method, and therefore it appears to be rather unsatisfactory. And even in Rutershauser's first really serious write-up of it in 1959, which occurs in the NBS publication, it's still described in those terms, and most of the examples done are of full matrices. And the subsequent history really is the gradual refinement of this crude algorithm, the speeding up of convergence, the shortening of the amount of work in each step, and finally the dealing in the most satisfactory way with complex conjugate pairs of eigenvalues of real matrices, and it's that I now want to sketch. Well, the first point to see is this speed of convergence is extremely unsatisfactory, because if we have a poor separation, some of the subdiagonal elements are going to go to 0 really quite slowly. Can we do anything about that? And the answer is that we can. And we first of all think in terms of a slightly modified algorithm in which we do not factorize A1 itself. We factorize A1 minus K1i for some K1, and then we multiply them together, add back the K1i, and we get A2. And we find, just as before, that A2 is still Q1H, A1, Q1. So it's still a similarity transformation of the first matrix, though of course the Q1 will be a different matrix. The actual Q1 you have will depend on the shift. So we now have a modified, possible modified algorithm. The general step is AS minus KSI equals QS RS, RS QS plus KSI is that equal to AS plus 1. Now, if we think of what happens in one iteration of the unshifted algorithm, really what we did was essentially to reduce unwanted elements by a factor lambda I over lambda j. And if you analyze the process a little more carefully, you see generally what is happening is that those in the last row, for instance, the one in position j is diminishing like lambda n over lambda j. It gets diminished by roughly that factor in one iteration. Certainly that's what's happening towards the end of the process. So that if we could choose ks to be fairly near to lambda n, then in one iteration the elements in the bottom row would all be multiplied by lambda n minus k over lambda I minus k. If k was lambda n, then all the elements in the last row would be diminished very substantially in that one iteration. But now we have a clue as to how to do that, because we know that if we were to iterate with zero shift, that is, use the classical process for the moment, the last element would be tending to lambda n. And therefore, after we've been going a bit, we could switch over to the shifted process and use as our shift ANN. That would be fairly close to lambda n after a while. And then as soon as we use that as a shift, the thing will begin to gallop. And you can see the possibility of getting a much higher rate of convergence. So that was the first sort of crude suggestion, to use the shifted algorithm, perhaps use the unshifted for a while until it began to converge a bit, and then take, after a certain point on, the ANNS as the shift. Well, that turned out to be very much more satisfactory than we expected. And in fact, a quite remarkable thing was noticed quite early on, and that it was so effective that it really didn't pay you to have a preliminary unshifted stage. And all more recent versions of the QR algorithm have tended to use a shift all the time, though in fact in the current algorithms it's not found from the bottom element itself, but in a slightly more sophisticated way. Well, that's the first point, and it's really absolutely vital if the QR algorithm is to become a viable competitor with some of the better algorithms which existed. Still, even with that, it's still very unsatisfactory because of the vast amount of work needed in one iteration. Well, now we come to perhaps a key point in the advance of the process, and that is the realization that when A is of upper Hessenberg form, if A is a matrix of upper Hessenberg form like that, then this form is preserved under the QR algorithm, and it's preserved even if one uses shifts. In fact, the shifts don't make any difference to this point. The A minus KS, whatever the shift, will still be of upper Hessenberg form. So this is our AS there. Let's see that it will indeed be invariant. Well, first of all, we have to factorize that in the form of QS and RS. And as I mentioned in my first lecture, one doesn't normally do it in precisely this form. What you do is determine an orthogonal matrix, which is a product of elementary matrices, and you determine it in such a way that the pre-multiplication of AS by that product produces the upper triangular matrix. In fact, really what you do is QSH AS equals RS, and you don't obtain the QSH explicitly, you obtain it as the product of elementary matrices. Well, from the point of view of what we're doing at the moment, we can think in terms of plane rotations. How do we reduce this to upper triangular form? Well, we multiply it first by a rotation in the 1-2 plane, chosen so as to make that 0, and a rotation in the 2-3 plane, chosen to make that 0, and then one in the 3-4, and so on, ending up with a rotation in plane R, n minus 1, n, and then we have the upper triangular form. So we need only n minus 1 plane rotations. The QR factorization of an upper Hessenberg matrix is much simpler than the QR factorization of a general matrix. So we now have our upper triangular form, and to complete a QR step, we have to multiply on the right by the Q, which we'll do in factorized form. We first multiply by the 1-2 rotation. That forms linear combinations of these and brings back an element there. Then we multiply it by rotation in the 2-3 plane, forms a linear combination, bringing up an element there, and so on. And we see the upper Hessenberg form gradually returns. We've demonstrated that upper Hessenberg form is invariant with respect to the QR. Well, that is a pretty decisive step, because now the amount of work in one iteration has gone down from order n cubed to order n squared. And at this stage, we might as well notice one further thing, which is quite important from our point of view. What about the case when AS is symmetric? So far, we've been considering just the general case. In fact, my A's have been possibly complex. Well, here we see that if A2 is in fact a QSH A1 QS, and therefore if A1 is Hermitian, A2 is Hermitian, in particular if A1 is real symmetric, Q2 is real symmetric, and the whole sequence is real symmetric. So the QR algorithm preserves symmetry as well. Well, we've seen it preserves upper Hessenberg form, and it preserves symmetry. So in particular, if applied to a tridiagonal matrix, which is upper Hessenberg and symmetric, so to speak, then it will remain tridiagonal. So rather interesting to look at that. Here's a tridiagonal matrix. Let's do the QR algorithm on it. What we do, we multiply by rotation in the 1-2 plane. It replaces these by linear combinations themselves, makes that 0, and brings up a non-zero element there. And then we multiply by a 2-3 rotation, making that 0, and bringing up 1 there. So on. Finally that. And we'll end up, the R has three diagonal rows. And let me write it now in which a form in which you can still see it. The R you get would look like that. And now we do the transformations on the right-hand side to complete the QR transformation. We take linear combinations of the first 2 columns, linear combinations of the second 2 columns, linear combinations of the next column, and linear combinations of the next one. And it appears to have become upper Hessenberg instead of tridiagonal. But we know it remains symmetric. These have certainly become 0 because they've been linear combinations of 0. And therefore, in some magic way, all these must have, although you wouldn't be working with zeros, they must all cancel out and give rise to zeros. Now, a very important point arises in error analysis here. We have a rather general error analysis which shows, which proves certain stability properties about a whole class of orthogonal transformations. But an important thing about that is it proves relations between the matrix which will arise if you actually do the calculation. And the only thing it allows you to do, for instance, in the case of plane rotations, it does allow you to insert a 0 in the one element that you make 0 specifically as a result of that stage. But these elements don't become 0 for that reason. They don't become 0 directly as a result of taking 2 elements A and B, producing a cosine and sine form, and in such a way that they will vanish. The argument that implies these are 0 is a highly implicit one, and whenever that occurs, you must do the error analysis and make certain that in practice it will be all right just to put zeros in there and not to calculate them. Because all the error analysis says is that if you do the computation, getting the full upper Hessenberg matrix, that will be good. That will be almost similar to the given matrix. Well, it turns out in this case, that error analysis does go through and shows that even the computed values here would be negligible. But failure to do that analysis is quite serious, and algorithms which haven't worked have foundered just because they've overlooked that fact, because there's been assumption that orthogonal transformations are stable and you can do what you like with them. Okay, so you have the perhaps an even more pleasing fact that symmetric tridiagonal matrices are invariant with respect to the QR algorithm. And of course, you're really in business there because the amount of work in one step is very small. Well, we might at this stage then look at the symmetric QR algorithm because it's one of the ones that's actually in the handbook. There are algorithms TQL1 and TQL2. They do, in fact, take a symmetric tridiagonal matrix and apply the QR algorithm to it. And of course, it should gradually become upper triangular, but since it's symmetric, it means it gradually becomes diagonal. Just to review the point again, we saw that when we do the pre-multiplication to get the upper triangular form, it turns out to look of that form that it really does have non-zero elements there. However, I've already observed that when you do the right-hand transformations, all the things that appear to arise up here mysteriously disappear, and you find that that means that you don't really need these elements. So that although they do arise in practice, you don't need to compute them because all you ultimately want is the tridiagonal matrix which results from it, and you can get this just by using these pairs of elements, so the amount of work is even further reduced. The whole point about it, if you think about it, when you do the first transformation, you do a transformation on those, and it brings up an element there. Now that element is not altered in the other things, so you already know this, and so you already know that. Because you already know what that is going to be when you've done everything, because it's going to be symmetric. And so at the stage when you do the next transformation, which would involve doing sine and cosine in those two, you don't needn't do it because you know what the answer is going to be, and that means that you never use any of these elements here. Right. Well, we've nearly got the QR algorithm, but just the point to be explained, why is it the QL algorithm? Well, that's one of those things that really doesn't matter at all. It's tied up with the history of the publishing of that particular set of algorithms, and none of us can ever remember quite for certain how it ended up like that. But you can, instead of factorizing A into the product of Q and an upper triangular, you can factorize the product of Q and a lower triangular, and that's what happens to have been done in the published algorithm. I've worked so many years now with an upper triangular reduction that if I do it the other way, I always seem to get everything wrong. So I shall just do the QR algorithm. There is no difference in the algorithms at all. If the matrix was turned up the other way, you would get the same numbers, even the same round-offs. And so there's just no significance to be read into it. Well, what happens then with our tridiagonal matrix? It gradually becomes diagonal. It gradually becomes diagonal. These elements gradually disappear. And of course, we use the shift strategy. And at first, the strategy that used to be used was that, as you know, this is going to tend to the smallest eigenvalue. And so the idea was that after a bit, it would be a good approximation to lambda n. If you used it as a shift, this element would begin to vanish very much faster. And we began to suspect that we got superlinear convergence. And that particular form of shift was used for a long time. I, in fact, proved that if you do use this shift technique, then the process is usually cubically convergent, but can occasionally be merely linearly convergent. In theory, the set of matrices for which is linearly convergent of measure 0. The probability is 0, but it isn't, because matrices are not really random in practice, it's by no means of measure 0. And when a matrix is close, remember, it's only asymptotically cubically convergent, and when a matrix is almost of the form that would give linear convergence all the way, then it gives rather slowish global convergence for a long time, and it'll be a long time before it became cubic. So that although this is extremely effective in general, and you might do many matrices with that shift technique and get very high rate of convergence, in practice it has this shortcoming. And quite soon we settled on using a different technique. We take this 2 by 2 matrix here, find its 2 eigenvalues, and use as the shift the nearer one to there. Of course, as this gets smaller, that technique is obviously tending, the shift is tending towards this value here. That shift technique was used for a very long time and found to give extraordinary convergence in practice. Convergence of such ferocity that I think if we'd been told, say 15 years ago, that there would ever be a process that gave convergence at that sort of rate, I think we would found it difficult to believe. And after we'd been using it for a number of years, we gradually became convinced there must be some reason why it converged so well. And finally, I did manage to prove it. The interesting thing is if you just use this as the shift, then you can prove that this is a monotonically decreasing. If you use the shift that turns out to be more satisfactory in practice, you can't prove that, and in fact it's not true. And I think that was the thing that held us up for a very long time. The algebra is rather complicated, but one day, in a very more determined mood than usual, I did manage to prove that the product of those was monotonic decreasing, and once you spotted that, then you're home. The reason I think we didn't spot it before is because the algebra is rather heavy. I wouldn't attempt to do it now because I know I would get it wrong. But the interesting thing is not only does it show that it's globally convergent, that it's ultimately cubically convergent, but it does something much more important. It shows why it gets cracking so fast. You see, originally our idea was that we would use zero shift for a while and then move over to a shift strategy when we began to get somewhere. That's the only thing that made sense to start with. Quite soon we settled down to using the shift all the time. We found that it worked very well, extremely well, but on the whole, it seemed a rather unreasonable thing to do, because certainly in the early stages, the shifts are not really all that close to the eigenvalues. They lie in the spectrum, of course, that you know, but they don't appear to be very good. Well, what the proof shows is, in fact, if you take the product of these last two things, bn minus 1, bn, that is the modified ones, and compare them with the previous ones, it's not only monotonically decreasing, but the proof shows that this is less than that, and you get, as the coefficient here, a whole battery of products of cosines and sines. And if you examine those, you find that it's pretty difficult to avoid some of those cosines and sines being quite a bit less than 1. So not only is it monotonically decreasing, but right from the start, it's tending to take a fairly good hammering, and so that even with the initial shifts, which don't appear to have much sense, the global convergence is setting in remarkably well. Well, I've used these terms, global convergence and asymptotic convergence, though it's rather difficult to see precisely what they mean with a process which has such fantastic convergence. The average number of iterations is about 1.8, and it's hard to say which is the global bit and which is the asymptotic bit. You know, because of this fact, it always seemed to me very important to try and get some understanding of the global part of it, since you could scarce... one rarely uses the true cubic bit for more than half an iteration, if one can speak in those terms. Well, one of the reasons why it is so fast is because not only are you making this element small, but of course you're tending to soften the others up too. They're getting smallish. They're not galloping at the rate this one is. But when these become negligible, This is an eigenvalue, and you deflate just by leaving off the last row and column. So you have an automatic deflation, which is stable, and that too is, of course, an essential thing in the success of the QL algorithm. But now when you move on to your matrix of order 1 lower, you'll usually find that several of these are rather small. In particular, this one is quite small. So that although it's not too uncommon to take 6 or 7 iterations for the first step, it usually takes many fewer after that, and it's not uncommon for several of the last eigenvalues to come out without any iterations at all, and that's how you get this remarkable average. Well, I think we can say we really understand pretty fully now the symmetric tridiagonal QR algorithm. And this is the method which is most commonly used to complete the eigenvalue problem after you've reduced it to tridiagonal form. You remember we discussed yesterday it's the competitor, the Sturm sequence. That has the advantage of being highly selective. Now, one price you pay for getting this fantastic rate of convergence is a certain loss of control about the way in which you get the eigenvalues. If you were to use no shifts at all, convergence would be very slow, but except for very rare exceptions, they would be ordered, and you would get the smallest one out first, one of the smallest modules. But because you use shifts right from the start, and the first shift is just comes from this 2 by 2 matrix, and it's not very intimately related to any of the eigenvalues, the tendency is to find first the eigenvalue which is closest to that shift. You don't absolutely guarantee that that's the one you'll find, but that's the most probable one that will come out first. And the eigenvalues tend to come out sort of in a rather uncontrolled manner. And so usually, if you want any appreciable number, and you're going to get them by the QR algorithm, it's usually much simpler just to get them all and then to order them and take the ones that you want. And that is what is done. There are no versions of the QR algorithm in the handbook which just find selected eigenvalues. One other point, of course, this is, it may happen that after a while some other element here becomes negligible. If that happens, if it's negligible, we can regard them as 0 and the matrix splits, and you can find the eigenvalues of this part and then move on and find the eigenvalues of the other part. In practice, that often is quite important, particularly when there are a number of multiple roots in the original matrix from which that came, in which case quite frequently some of these will be fairly small. Not necessarily as small as you'd hope, having regard to the fact that with exact computation they should be 0. It's one of the disappointments of life. Well, the theory is really therefore quite simple in the symmetric case. Now we go over to the general case, and there we don't start with tridiagonal matrices, we start off with upper Hessenberg matrices. Now we immediately strike a snag here. Of course, I suppose 99% of all the eigenvalue problem solving that's done is done with real matrices. But you may have a real matrix, but that will not guarantee that you've got real roots. And of course, in general, we do meet quite a reasonable percentage of matrices which have some complex roots, very often mixed real and complex conjugate pairs. Now we see, if we start off with a real matrix and we use real shifts, all the if we like to determine the shift by means of A and N, or use this rather unlikely strategy of the 2 by 2 of this matrix, so if we use the bottom thing, we will only have real shifts. And therefore, in the case of complex conjugate roots, we can't possibly be choosing shifts very close to the eigenvalue and get the sort of superlinear convergence we're hoping for. If we use this 2 by 2 matrix, we will get, from time to time, complex shifts. But then, when we take a complex shift away from a real matrix, we've got a complex matrix. We decompose it. It becomes the Q and R are fully complex. We multiply by RQ, and starting with A1, we end up with an A2 which is a complex matrix. So that's a very unsatisfactory state of affairs. Naturally, with a real matrix, we would like to remain in the real field. Well, it doesn't look as bad as all that, because you say, well, if you have complex eigenvalues, what you should do, if you decide on a complex shift at all, is to do two steps. One with the shift k, and one with the shift k bar. And if you go through the sort of analysis I did of the QR algorithm in the first instance, you find that if you did that exactly, although A2 will be complex, when you formed A3, all the complex parts would magically disappear and cancel out, and you'd come back to a real matrix. Well, that looks very nice. You say, well, QR algorithms are stable. You say rather quickly. So if you do it in practice, A3 will have small imaginary elements. Well, if you do, you'll be completely wrong, because the error analysis doesn't say that. It says that A3 will be exactly similar to something which is close to A. It doesn't say that A3 will be close to the matrix that you would have got by exact computation. The matrix you would have got by exact computation will be exactly real, and if this second result were true, we would have, in practice, a matrix with negligible elements. Now, this is not just hair splitting. In fact, if you do this process, you will find that quite often the A3, so far from having negligible elements, will have imaginary elements which are as large as the real ones. It will still have the eigenvalues okay. It will still be almost exactly, it will still be exactly similar to something close to A. But the one thing it will not be is real. And so this process is not possible. And so we now come to the great point of Francis', excuse me, known as the double Francis algorithm. And the point was Francis discovered how to do two steps of the QR algorithm in such a way, using complex conjugate shifts, or possibly just two real shifts. He discovered a way of doing the process by an entirely different technique, which remained completely in the real field. Perhaps, although he didn't do that, perhaps I'll just describe it first in connection with the real symmetric case. Now, supposing we are... He, in fact, put forward a process for doing the QR algorithm with a shift, which, oddly enough, didn't necessitate taking that shift from the matrix A. Let's analyze the process then. If you really did the shift, you'd have A minus Ki equals QR, RQ, plus Ki. That's A1, and that's A2. And we know that A2 will be equal to Q1H, Q1T, it's going to be real at the moment, A1 times Q. And so that, in fact, A1Q is equal to Q1T A2. And then he made the observation, which, in fact, I proved this result when I was talking about the reduction of a general matrix to triagonal form. He observed that if you're given the first column of Q1, sorry, that's Q there, given the first column of Q, then, and the fact that A is tridiagonal, then everything is determined. So that if you went from A1, which is tridiagonal, to A2 is tridiagonal, and they satisfied a relation of this kind, if you did it by two different ways, but if the orthogonal matrix you used in both cases had the first column, then the whole matrix would be the same. And from this observation, he was able to derive A2 from A1 without ever forming A1 minus Ki. Well, having done that, well, this is the way I like to describe it at the moment, though in fact he didn't do this. He thought of it the other way. He similarly found how to go from A1 to A3 In the general case, where A is Hessenberg, where A1 and A3 are Hessenberg, using two complex conjugate shifts by a technique which is really apparently quite different from the QR algorithm itself and is based on this observation. Well, there isn't time to start that now, and I will go into it when I discuss the details of the implementation of the QR algorithm. Right?